What would the process of drilling through the Earth look like? To penetrate the Earth's crust, mantle, and core, a drill would need to be made from specialized materials capable of withstanding enormous heat and pressure. Although humans have never drilled through the Earth, scientists can make some predictions about this process based on data from previous drilling projects. The Earth's diameter is 12,756 kilometers, so drilling through the planet would require a massive drill and decades of work. The first layer to drill through is the Earth's crust, which is about 100 kilometers thick, according to the United States Geological Survey, USGS. Atmospheric pressure would increase as the drill goes deeper underground. For every 3 meters of rock, atmospheric pressure rises by roughly 1 unit, equivalent to sea level pressure, says Doug Wilson, a geophysicist at the University of California, Santa Barbara. The deepest artificial hole ever drilled is the Kola Super Deep Borehole in Russia, which reaches 12.2 kilometers deep. At the bottom of this hole, the pressure is 4,000 times that of sea level. It took scientists nearly 20 years to reach this depth, and they were still more than 80 kilometers away from the next layer of Earth, the mantle. The mantle is a dense, dark layer of rock that is 2,800 kilometers thick and plays a significant role in tectonic plate movements. The boundary between the crust and the mantle is called the moho. Scientists first attempted to drill deep into the ocean floor to reach this boundary in the 1950s and 1960s with the Mohole project, but they failed. One significant challenge is that the hole created in a planetary drilling mission would collapse unless a continuous supply of drilling fluid was pumped in. When drilling for oil and in deep-sea projects, this fluid is a mixture of mud with heavy minerals, such as barite. Wilson explains that the weight of the fluid helps balance the pressure inside the hole with the pressure from the surrounding rock, preventing collapse. Drilling fluid has two additional functions: cleaning the drill bit to prevent sand and gravel from sticking to the machinery, and cooling the bit. However, keeping the drill cool in the Earth's deepest layers would be nearly impossible. For example, the mantle's temperature reaches up to 1,410 degrees Celsius. According to Wilson, stainless steel would melt at such temperatures, so the drill would need to be made from expensive, specialized alloys like titanium. After penetrating the mantle, the drill would eventually reach the Earth's core at a depth of about 2,900 kilometers. The outer core is primarily composed of nickel and liquid iron and is extremely hot, with temperatures ranging from 4,000 degrees Celsius to 5,000 degrees Celsius, according to the California Academy of Sciences. Drilling through this molten mixture would be particularly challenging. This process would introduce a whole host of problems, says Damon Teagle, a professor of geochemistry at the University of Southampton. The superheated outer core could melt the drill bit unless cold water was pumped down. Then, after drilling 5,000 kilometers, the drill would reach the inner core, where pressure is so immense that despite the searing heat, the nickel and iron remain in a solid state. Teagle says the drill would need to withstand pressure around 350 gigapascals, which is 350 million times atmospheric pressure. Throughout the entire process, the Earth's gravitational pull would tug the drill toward the core. At the very center, gravity would resemble that experienced in orbit, resulting in a state of weightlessness. This occurs because the Earth's mass would exert equal gravitational force in all directions, Wilson explains. According to Teagle, if all these obstacles were overcome, the biggest issue upon reaching the center would be that there is still a long way to go to the other side. As the drill continues toward the other side of the planet, gravity would shift in response to its position, pulling it back toward the core. The drill would have to resist gravity as it ascends toward the surface, passing through the outer core, mantle, and crust, the reverse of its initial descent.